marathon session, revision session, where we are going to learn the next few concepts about waves, and we all have studied what waves are, and we have built up upon the concepts of waves. We started with waves on a string, then we went to sound waves, then we have gone to electromagnetic waves or light waves. We have also spoken about interference of waves. Now today we are going to talk about Young's double slit experiment as well as diffraction. So bending of light, spreading of light, the formulas and some questions from previous years, and also the most famous experiment, Young's double slit experiment, and some interference related questions from previous years. All this with me, Shreyas, your master teacher for physics at Vedantu, going live. Hello Priyanka, Saurabh, Science Priya, Aishwarya, Shabana, welcome Yalini, welcome Minyanarthi, welcome VK, welcome everyone out here. Hello, hi. Join in. Yes, welcome. And some of you started off your greetings in some very nice languages like Indonesian. So we had Japanese, greetings by Kirito last couple of days, and then now we have Indonesian. God knows which all other languages we are going to learn, and I'm pretty sure we are going to learn how to say hello, bye, and other basic stuff in many other languages for sure. Welcome. Hello Jaya. Hello everyone. Okay, Science Priya's real name is Priyanka. Okay, I'll keep that in mind. Yes, Japanese konnichiwa. Yes, so Kirito had messaged saying that he has his school exam, so he'll be watching the replays. So all those people who are watching the replay, watch it completely. And let's begin with the session. And I'm Shreyas here. I teach physics not just on YouTube but also on the regular platform of Vedantu. And I have been training kids not just online but also offline before this. And after I was exposed to this beautiful world of online teaching, there is no going back. And I love being here on YouTube and also on Vedantu's platform because I can reach to so many kids just sitting at one place. Earlier I was so limited in terms of the reach. I could hardly cater to maybe few hundred students per batch or something like that, but now I can reach to thousands of students, and that's what makes me really proud, and I'm so glad that it makes a difference in so many of your lives. Hello Ankit, welcome. Hi Chandresh, welcome. Hi Sparsh, join in. And guys, in case you're new and you want to follow me, follow my stories and follow my posts, you can do so on Instagram. That's my handle, Shreyas_Vedantu on Instagram. And let's not forget to subscribe to this channel in case you're new and you haven't done it yet. And if you have not yet liked the video, go smash that like button out there, because I need all your energy, all your support, all your love to conduct this lecture for free on YouTube. So go ahead, smash that like button out there. Now, in case you have missed any of these classes on waves, please go ahead, check out the playlist, check out the past videos, you will find it there. Waves, we started with transverse longitudinal, then electromagnetic. Yesterday we did standing waves, Doppler effect, beats. Today we are going to do Ydse interference and diffraction. Tonight at 10 o'clock, do not forget, we are starting modern physics. Yes, a very late night session. So have your dinner after this session and I'll see you at 10 o'clock as well. And tomorrow, same thing, 7 o'clock, you're going to have a mock test discussion of physics, and then continued at 10 o'clock, modern physics, atomic structure, X-rays. And then on Saturday, 7 o'clock, nuclear physics, and Valentine's Day special on Sunday. What is it? I don't know. Let's see. Okay, so let's begin with the session. Now, I'm pretty sure most of you remember what interference is. Hi Tanmay, long time no see. Hi Manjunath, hi Jaya. Hello everyone. Hi Saurabh. Welcome. So, interference is when two waves mingle with each other, meet each other, they superimpose over each other, and they produce interference. And we have seen two basic types of interferences. When the two crests or their two troughs meet together, that's constructive. And when the crest, like this one, now when the crest and the trough meet together, they cancel out each other, that's destructive interference. So understand, when the crest of one wave meets with the crest, the trough of one meets with the trough, the resultant wave which is produced. Now, be it wave on a string, be it sound wave, be it light wave, or any other wave. These are general rules, by the way. So if this wave has amplitude A1, this wave has amplitude A2, then the resultant wave has an amplitude of A1 plus A2. That's the net amplitude, and the phase difference between them is 0, and they are said to be in phase with respect to each other. That's said to be in phase. Similarly, we have seen that if the crest of one meets the trough of the other and vice versa, so if each wave has amplitude A1 and A2, the resultant wave may or may not cancel each other, depends on their amplitudes. If they are equal, they will perfectly cancel out each other, but for most of the other times, it will be the modulus of A1 minus A2, whichever is bigger minus the smaller amplitude. In those cases, the phase difference between them is pi radians, and they are said to be out of phase with respect to each other. I hope all the minions, I hope all the V enthusiasts, I hope all the students out here remember this, and in case you had forgotten, this is a quick recap of all of that. I'm very fine, Tanmay. Thank you very much. I'm very good. Yes, very good, Manjunath. Smash the like button. Very good, very good. Excelente, guys. Now, I had also mentioned about what if the crests and the troughs are not perfectly aligned? Maybe there is some, weird amount of difference between the waves. So maybe the two waves originate from some point, but their wavefront, the first wave that is going to come, all right, from both these waves, all right, the first pulses that are going to come from both these waves, they have some difference in the path. Both these waves come from there, but there is some difference in the path. Like both of them are not coming together. So there is something called as the path difference, and this path difference produces interference because there is going to be some phase difference between them. Recollect, the phase difference was 2 pi divided by lambda into delta x. I have given you this formula. So imagine if the path difference is one wavelength is 2 pi radians. Keep this in mind. So if delta x is lambda goes, and del phi is 2 pi radians. So both will be in sync because their crests and the troughs will match together. But if at all the phase difference is pi radians, that means delta x will be either lambda by 2 or 3 lambda by 2 and stuff like that, because you can just visualize this. If delta x is lambda by 2, lambda goes, 2 goes, only pi will remain. So that will be out of phase. And then finally I had told you the resultant amplitude is given by A1 square plus A2 square plus 2A1 A2 cos of del phi, the whole thing under the root. That was the formula for the resultant amplitude. Looks very similar to vectors, where you draw one vector here like this, draw another vector here like this, and this would be the resultant wave's amplitude, where remember this over here is the angle between the vectors. That's how it is. It's at the end of the day vector addition. I hope this is clear. Yes, Omkar, I'm going to do diffraction as well by the end of the class. Yes. Hi Princey, good evening. Join in. Yeah, interference of thin films, Ankit, is not there. It's deleted long time back from the JEE syllabus. So some people still teach it. I don't know why, but it's not there. Even in mains, even in advanced, even in bits. Okay. So Hariharan, my name is Shreyas and I teach physics obviously on not just on YouTube but also on the regular platforms. All right. So let's get going with the next part. Now that's the main part. So here comes the main part of today's class. Optical path difference. Now imagine two rays of light, okay, starting simultaneously, the blue one and the maybe brown one. The blue one happens to pass from a glass slab and the brown one does not pass through any glass slab. Now they both go through a convex lens and they merge on the screen at the focal point. My question to you is, which ray will reach the screen faster? Is it the blue one or is it the brown one? Which one do you think will reach the screen faster? Is it the blue one or is it the brown one? Come on, think about it. Hello Anthony, welcome, join in. Come on, think about it. Is it the blue one or is it the brown one which will reach the screen faster? Very good. It will be the, Aishwarya says, the brown one. Yes, yes, Science Priya, yes, Shabana. Oh, Shabana, no, it's not the blue. The blue one is going to pass through the glass slab. And what happens? The speed of light reduces once it enters a denser medium. So the blue one is going to slow down, and meanwhile, the brown one is going to continue ahead. And by the time the blue comes out, the brown has already gone a little bit ahead. So the brown is going to reach faster than the blue one. So I hope you see there is some kind of a path difference which has been created. Don't you see that? There is some kind of a path difference which has been created. So understand what is that path difference. That can be easily found out. Let's say I give you some kind of data, like for example, this is the thickness of the slab or the length of the slab, all right, and the speed of light outside is c, but the moment the light enters inside, understand the speed of light will become c1. It's going to change. And what's the value of c1? That's not difficult to find. Speed of light in air upon speed of light in medium is the refractive index. Therefore, c1 is c divided by mu. Makes sense. The speed of light is going to reduce by mu times. Cool. Now, once we know that c1 is going to reduce because of the refractive index, let's just try to figure out how much time does this blue light spend inside. Let's say I call this ray number 1 and ray number 2. How much time is spent inside the slab? So time spent inside the slab will be distance divided by speed, and speed we just calculated it to be c by mu. That is the time spent inside the slab. Now my question is, in this time, how much did ray number 2 cover? How much did ray number 2 cover? Let's figure that out. The distance traveled by ray number 2 will be speed of ray number 2. Well, that's not going through anything. It's going through air. So it must be c. And for how much time? This much time. The time spent inside the slab by the other ray. So that will be c into L mu divided by c, which is going to be L mu. Now this is very interesting. This ray 1 covers distance L. In that same time, ray number 2 covers a distance of mu L, mu times more. So I hope you see that. It's covering more distance. So hence the path difference will be L mu divided by L, which is L common into mu minus 1. So that is very, very important. This is the path difference which is produced because one of the rays passes through a medium, a denser medium. Is that clear? Yes, Omkar. It's the same thing. Optical path length derivation is exactly this. So you can say this is now the optical path length. So one can think as if, this is that extra length this ray has to travel in order to come at the same point. That's how you can think about it. All right. So this is another way to look at it. Omkar, I hope that's clear. Cool. I hope this is fine, guys. Everyone clear about this? Ankit, don't worry. Hold your horses. Don't worry. We're going to come to Ydse. Hold on. Okay. So now that we know about, interference and how you can create path difference by slowing down one of them. Now let's think about what kind of sources are needed for interference. You might think it's not a big deal, but actually it is. Now in light, there are two kinds of sources. Actually, even in sound, you can have those sources, but more specifically in light, it makes a big difference. There is one thing called as the coherent source, the other thing called as the incoherent sources. Coherent means a light source which emits, all right, or two light sources which emits wave fronts or waves together and in sync. Meaning, if I know source 1 is emitting a crest right now and if I know that other source is also emitting a crest right now, I am sure that whenever source 1 emits crest, then that time source number 2 is also going to emit crest. It's not going to change. The relationship is not going to be different. If this one emits trough, I know for sure this is going to emit trough. So they are in sync. It's not like I'm emitting crest now, you are emitting crest now. After some time, when this guy, source 1 is emitting crest, this guy changes his mind and he's like, oh, okay, I'm going to emit a trough. No, he's not going to change his mind. They are going to be always in sync, just like the soldiers doing a march past. All right. So now wavefront is basically, think of it when you produce sound, all those points where the sound reaches simultaneously. So if there is a source, all those points where the sound reaches simultaneously, that is basically, that envelope is called as the wavefront. Now, usually if I take two bulbs, they won't be coherent. Yes, you take two torches, you take two candles, you take two identical bulbs also, no matter what you do, they are never going to be coherent. In fact, they are always going to be incoherent. And the meaning of incoherent is, they are random. When source 1 is emitting crest, maybe source 2 is emitting trough. After some time, when source 1 is emitting crest, maybe source 2 is emitting crest. And it keeps changing. It's random. They are not in sync with each other. So you can see the wave patterns will look very weird. Sometimes one source is emitting something, the trough is matching, sometimes the trough is not matching, sometimes the crest is matching, sometimes there is nothing. It's random. Sometimes it is not even emitting. So guys, understand, usually every source around you is incoherent. What is it? Every source around you is generally incoherent. They are not in sync. If you take any source and any other source, there will always be incoherent sources. Keep this in mind. Is that clear, everyone? Now, here comes the problem. Imagine if I want interference of waves, I need to be sure how these two waves are with respect to each other. I need to know that, okay, at this time there was a crest coming, and at this time there was a crest coming from here. So I know maybe later on at some point of time, if there is another crest coming here, I know for sure there is a crest coming here from the other wave. But if that is not true, in case of incoherent sources, then how am I going to figure out what kind of interference is going to happen? That will be unpredictable, because what might come from the other wave is completely unpredictable. Maybe nothing comes from the other wave. So that means you need the sources to be coherent for interference to happen. I hope that makes sense. Good evening, Delhi Moni. So imagine you have two light sources, and let's say the distance from that source to a particular point, let's say I call that point as P. Alright, this source travels a distance of L1, this source travels a distance of L2. So both of them are not going to meet at point P simultaneously. The light from this source and the light from this source is not going to come simultaneously. There is going to be some path difference, and that path difference will be L1 minus L2, whichever is bigger, and that in turn will cause some phase difference, which is 2 pi by lambda into L1 minus L2, or the path difference. Now keep in mind the resultant intensity at point P. Alright, the resultant intensity of point P will depend on intensity of both these bulbs, and I have given this formula to you even in sound waves or in just transverse waves. The resultant power or intensity will be I1 plus I2 plus 2 root I1 I2 cos delta phi. That cos delta phi is not inside the root, it's outside the root. This is the formula. This is the formula for the resultant intensity at point P. This comes via vector addition of amplitudes. Do not forget, in case you have forgotten, let me mention this. Intensity is directly proportional to the amplitudes square. Keep this in mind. Intensity is proportional to amplitude square. That's how this formula comes. In fact, this formula, keep in mind, is only applicable for coherent sources. Yes, it's only applicable for coherent sources, because it is predictable. I know what is the phase difference. I know what is the part difference. I know how much will be the difference in the phase between the two waves because they are predictable, they are in sync. Now, is sun a coherent source? No. So, how do you get a coherent source? We'll come to that. But if these two sources are incoherent, then what is going to happen is sometimes their crests will arrive together, sometimes this crest and this trough will arrive together. So you will see sometimes there will be constructive interference and sometimes there will be destructive interference and sometimes there will be some intermediate interference, and it will average out over time. Constructive, destructive, constructive, destructive. So it will average out. So remember, when it is constructive, del phi is 0, cos 0 is 1, and when it is out of phase and stuff like that, so it's going to get all kinds of values. This del phi, it will get 0 value, it will get pi, it will get 2 pi, it will get pi by 2, it will get 3 pi by 2. So this del phi is going to get all kinds of values. I hope you get that, because all kinds of possible phase differences are possible, because of which the average value of that cos term will be 0. It will go away, it will vanish, and what you're going to have is the intensity at point P will be just I1 plus I2 only, that's it. And this is true when they are incoherent sources. Incoherent sources. Or basically they are not coherent. I hope this is clear. I hope this is clear. Yes. I hope this is clear. Is that understood, everyone? Is that understood, everyone? So very important that when coherent sources are mentioned, only then use this formula. When it is non-coherent or incoherent, they are not coherent, then use just addition of intensities. That's how it is. And these kind of questions have come in JEE. Alright, so keep this in mind. Now I know you might be thinking, how do I get coherent or incoherent sources? So let's come to that. I hope you have noted down this formula. The best way to get a coherent source, because usually whatever is there around you are non-coherent, is derive those sources. Yes, derive those sources. Imagine you have a source which emits light. Alright, so let's say you have, for example, alright, you have a source. Alright, this is a source of light. Alright, it emits light from here, and that light passes through a slit, it will spread. We'll talk about spreading later on, because that's called as diffraction, and we're going to deal with diffraction at the end of the class. For now, let's just assume it's going to spread. And what is going to happen when the light spreads? Understand, there are going to be wavefronts created like this, crest troughs, crest troughs, crest troughs, and they are going to land on these two slits simultaneously, and again from these 2 points you're going to see the light is going to spread like this. So these two are going to be in sync because they are at the same distance, and whatever starts from here, if a crest comes from here, that crest will land on both the slits simultaneously. So these two slits will behave like the secondary sources. They will behave like the secondary sources, and they will always be coherent. They will be always coherent sources. These secondary sources are also called as, derived sources, because they are derived from this particular primary source. So a primary source has created two derived sources which are in sync because they are coming, because the wavefronts are simultaneously reaching both the slits together. I hope that's clear. Very good. I can see some bulbs lighting up there. Very good minions, very good V enthusiasts. So that's how you get a coherent source. Shall we do some problems now? Yep, let's do some problems. Cool. Okay, cool. Now look at this. This is a very good, cool simulation of how derived sources are created. Look at this. There are two slits out here. Forget what happens over here. But look at this. Wavefronts are reaching two slits together. These are ripples in water. And you will see that when the ripples reach here, they create two wavefronts separately. They are in sync. So these two are two derived coherent sources. Please keep this in mind. Although the topic is light, whatever I teach you here is also applicable for sound waves or any other waves. because this is general wave theory. Just that we are talking about light more exclusively in this chapter otherwise. Alright. Yes, Aishwarya, wavefronts are something like equipotential surfaces, correcto. And rays of light is like electric field or magnetic field or gravitational field. You can think of it vaguely like that, correct. Yes, Science Priya, you have seen this in the session of does reality exist or not? If you do not see it, and if you have not seen that lecture, I request you to see that lecture for sure. Yes, cool. Let's get going with questions. 2019 JEE question. Two coherent sources produce waves of different intensities. Okay, two coherent sources produce different intensity waves and they interfere. Okay, when they interfere, the ratio of the maximum intensity to the minimum intensity is 16. What is the intensity of the individual waves which are interfering? Some answers are given, options are given. Let's figure out which of them is correct. Let's not look at the options. Let's try and solve this without looking at the options. Oops, by mistake I went to the answer slide. I'm so sorry, guys. Okay, let's do this. Okay, let's just pretend that we do not know the answer and let's solve this. Now, what is the formula for intensity? The formula for intensity is I1 plus I2 plus 2 root I1 I2 cos del phi. Okay, cool. Now, let's say maximum intensity is produced. Maximum intensity means del phi is 0. So I max, alright, I max will be I1 plus I2 plus cos 0. Cos 0 is 1. So it will become 2 root I1 I2. That's what you're going to get, which is nothing but root of I1 plus root of I2 whole square. I hope this makes sense. A plus B whole square is going to give you this expression. Next, when del phi is pi radians, that's when you're going to have the minimum intensity. Look at that. So they are out of phase. So then I minimum will be I1 plus I2 plus, okay, wait a minute, cos of pi, cos 180 is minus 1. So bring that minus here and it will become minus 2 root I1 I2 and just write it in A minus B whole square. So root I1 minus root I2 whole square. That's what I'm going to get. Now, according to the given question, they have given I max by I min. Now, I max divided by I minimum is given to be 16. Alright, 16 is to 1. So, this by this basically. So, it will be root of I1 plus root of I2 divided by root of I1 minus root of I2 whole square is 16. This divided by this, guys, that's it. I've just substituted it here and whole square. So I'm going to get root I1 plus root I2 divided by root I1 minus root I2 is going to be 4. All right, 4 by 1. Now there is a property called as componendo dividendo. So using componendo dividendo, which says if A by B is equal to P by Q, then A plus B divided by A minus B is P plus Q divided by P minus Q. Numerator plus denominator upon numerator minus denominator. That's what is componendo dividendo. So when you do that, this plus this is going to give me 2 root I1 and this minus this is going to give me 2 root I2 and that's going to be 4 plus numerator plus denominator upon numerator minus denominator. So that's going to give me root I1 by root I2 as just 5 divided by 3. Therefore, I1 divided by I2 is going to be 25 divided by 9. Lot of maths, but yes, very good. Some of you got it. Yes, 25 by 9. Yeah, very good, very good. Yes, got it. So this is how you are supposed to do it. This is a proper method of doing this. So all depends on this formula which I just gave it to you. Intensity formula, which is very identical to the amplitude formula, guys. Okay. So that's how you do this problem. Let's get going to the next one, 25:9. Well, 2003 question. Let's see how many of you get this. To demonstrate the phenomena of interference, we require two sources which emit radiation. Which of the following is correct? Think about it carefully. Nearly same frequency, of same frequency, of different wavelengths, of same frequency and having a definite phase relationship. Only one of them is correct. Only one of them is correct. Yes, Prakash, very good, excellent. Yes, Omkar, excellent. Aishwarya, no, I don't think so, that is correct. Come on. Yes, the answer, guys, is going to be D. You need it not only of same frequency but also to make sure that there is a particular phase relationship. Meaning, if this guy is producing crest, I know this guy is producing trough. I know later on also if this guy produces crest, the other guy is going to produce trough. So I need to be sure that their phase relationship does not change. Else, just making the frequencies equal is of no point. Understood, guys? Excellent. Let's get going ahead with the next question up. All previous year questions, guys, I want you guys to gain confidence because see, I'm teaching you theory, we are doing questions. Teaching you theory, making you do questions. So I'm pretty sure solving these previous year questions, you are going to feel confident that yes, I can crack the actual JEE examination. All right, here's the next question up on your screen. Come on, come on, come on. Let's do this. Beautiful question on coherent as well as incoherent sources. Let's see how to do this problem. Now, well, n waves, identical waves of equal intensity interfere. First time coherently, second time incoherently. What is the ratio of the resultant intensity? So guys, I'll tell you what. Imagine there are n waves like that. 1, 2, like that, dot, dot, dot. N waves. Each of them have amplitude A0. Okay, each of them have amplitude A0. Now, think about it. First situation 1, where it is coherent. If it is coherent, then what is the resultant amplitude? Well, if all of them meet coherently together, then the resultant amplitude will be A0 plus A0 as n times. There will be n times. So you are going to get n A0. I hope that's clear. You are going to get the amplitude as n A0. Now do not forget one more thing. If the intensity of each wave was I0, and keeping in mind intensity is directly proportional to the square of the amplitude. So if the resultant amplitude becomes n times, think about what the resultant intensity is going to become. Square times. So it is going to become n square times of I0. So when the sources are coherent, the resultant is going to have n square times of I0 intensity. Is that clear, everyone? Now think about it. When the sources are, alright, incoherent. When the sources are incoherent, then what happens? I told you guys, just add the intensities. Yes, just plain simple scalar addition. Don't worry about phase difference. That's it. So guys, the resultant intensity that time is going to be just n times of I0. Yes, that's going to be just n times of I0. Now what is this divided by this? N square I0 divided by n I0. That's what we want. N square I0 divided by n I0. Obviously that's going to be n, and that's the answer. So you can see how beautiful this question is. Very good, very good. Some of you got it. But do you understand the essence of this question? There are two kinds of addition. One, when the sources are coherent, their amplitudes at, and when their sources are incoherent, that's when their intensity is at. Be careful. Alrighty, let's get going with the next question. As the answer, by the way. Excellent, Vinians, and if you are loving these questions, do not forget to hit the like button out there. Go smash it, and if you have forgotten to subscribe, in case you are new, go hit that subscribe button right away. Alright, let's get going to the next question. Looks crazy, but do not get scared. Two light waves having same wavelength in vacuum are in phase initially. Okay, so two light sources or waves have same wavelength and they are in phase. One of the wave passes through a medium of refractive index n1, length l1. Another one travels through refractive index n2, length l2. What is the phase difference between the two waves? Options are given. Let's try to figure it out. Yes, let's see how to do this. Okay, I don't know which one will be correct. Oops, I'm pressing it. Okay, I'm pressing it more than what is required. So it's automatically going to the next slide. No problems. Let's see how to do this. That's more important. Understand, I told you, if a light ray, goes through some glass medium, of refractive index, let's say n and length l, then you can assume that this same light, is as if going through a larger path, because it is going to go slowly, of length l times of refractive index. Keep this in mind. If a light ray goes through a glass slab of refractive index n, then it is as if it's going with the same speed in air but a larger distance of ln. Keep this in mind. So guys, think about it. One ray which is going to come, it's going to travel a path length of L1 N1. The other ray is going to travel a path length of L2 N2, and both of them are going to have some path difference out here, and that delta x, is going to be whichever is bigger and whichever is smaller. So L1 N1 minus L2 minus L2 N2. I hope that makes sense. So that's the path difference, and hence guys, that phase difference will be 2 pi divided by lambda into this path difference, which is L1 N1 minus L2 N2. Is that okay guys? Understood. Yes, Baptisha Paul, very good, Umkar. Yes, these are all questions by Reddy from previous year questions. Like you can see, I mentioned the year number also so that you get confidence, and I want you to see how each topic, after learning each topic, how you can directly apply that theory on those previous year questions, because you need that practice in the last few days, and also you need to gain that confidence and see those methods as well. So that's the answer. All right, let's get going to the next part. Now I'm going to go to Young's double slit experiment. Okay, Young's double slit experiment. Now what is Young's double slit experiment? What is diffraction? And I know before going there, I know many of you who are very new have at least one of these problems, like probably you're not able to solve all the questions, maybe you have doubts and nobody to clear them, or things like, you have a lot of stuff to cover in the last few days and you don't really know how to do this, you don't know how to exactly manage the time, or you don't know what the schedule should look like in the last few weeks, what is it the toppers do, or maybe you're not able to manage boards as well as your regular studies simultaneously. So for all those kind of students who need that hand holding, who need that kind of push, who need that kind of competitive spirit, who want to feel amongst who want to feel that healthy competition amongst all the other students, like-minded students who want to crack the examination, also all those people who want that dedicated mentorship, who want a mentor who is going to solve all their doubts from morning till night, that too instantaneously, and who want to give a lot of mock tests and want their discussions to be done because you want to know what your mistakes are, then don't worry guys, we have covered all of these things in a crash course which starts Monday. And the best part is, this crash course has too many sessions which covers all the syllabus of 11th and 12th. That's important. And morning till night doubts inside the class as well as outside the class. And the best part is guys, you also have 15 full syllabus and 5-part test series, so that you identify, learn from your mistakes, so that you do not repeat them in the final examination. You actually get the feel of the final examination, and all India ranks are given to you in this crash course and all these crash tests. Yes, you get an all India rank score, so you know where you stand approximately. And all of this is running on sale now. Usual price is 10,000, usual discount is 20%, but today, because of, I don't know, Valentine's Day sale and maybe the love is in the air, so you are going to get 30% discount, and that's a huge discount, and it's limited time, like most of you know. So go grab that offer right away, because it's going to slide from your hand very quickly if you do not grab it fast. So go grab it. 7,000 rupees, that's the crash course price for this amount of huge compact package that you're going to get. And obviously you can get the discount only if you use the coupon code SHCC. So please check out the link which is there in the description box below to know more details about this. All right, now, so let's get going about Young's double slit experiment, and that's what we're going to start now. Okay, some of you saying YDSC is your favorite. So Aditya, hold on, we have not even come to YDSC, we just came just now. So we're going to see all the formulas, and probably those questions will obviously get answered right now. All right, so let's begin. Now, what is YDSC basically? Young's double slit experiment. Long time back, Young wanted to go against Newton, and he proved to Newton that light has wave nature. Newton was of the belief that, you know, light has particle behavior or particle-like characteristics. This was a groundbreaking experiment because it clearly proved that light behaves like a wave. Very, very interesting. Now, what happens is that when light passes through two slits, we have just seen they behave like two derived sources, both of them in sync and together emitting wavefronts together. They are coherent in nature and they both emit wavefronts. Now, like you can see, some places these wavefronts, their crests or their troughs meet together, and that's where you are seeing the constructive interference. I hope you can see that constructive interference out here. And some places the trough of one will meet with the crest of the other. That will be destructive interference. I hope this is clear. Now, this, imagine, is a light source. There are two slits, and the light which spreads from these two slits interferes constructively and destructively in these regions. And to observe where it interferes constructively and destructively, you place a screen in front of it. So on that screen, what you are going to observe is all those places where the light interferes constructively. There will be a bright region over there. Constructive means addition, intensities will be more. And some places, crest and trough will cancel, so you will not see light falling in those places. So those will be relatively darker, and this is how it's going to look like. Observe this, the two sources of light creating waves, secondary sources, and you will see some places. Look at this, this is the screen. The waves, as soon as they reach, some places there is constructive, that's bright. Some places it's dark because light did not reach there, or I can say it has interfered destructively. I hope this is clear. I hope this is clear. Okay, I hope this is fine. So you can see the interference pattern forming on the screen. By the way, Young's double slit experiment is not just limited to light. It can happen with matter waves, it can happen with earthquakes, it can happen with sound waves, it can happen with any other waves which you can talk about. Alright, but here we are specifically talking about light waves. Look at this beautiful pattern. Two slits out here, light is entering. Very hypnotic, I must say. And you can see some places it is constructive. So on the screen you can see that bright region, and on the screen you can also see the dark regions out there. Dark regions means destructive, bright regions mean constructive, and from one dark to next dark, that's called as a fringe width, or from one bright to next bright, that's also called as the fringe width. So these are fringe widths, dark to dark or bright to bright. Just like wavelength, these are called as the width of the fringe. And these things depend obviously on the distance between these two slits, and distance between these two slits and the screen, and also the wavelength of the light which has been used. So it depends on all these parameters. Distance between the slits, that distance between the screen and the slits, and the wavelength of light, of course. All of this. Yes, it's looking very awesome. I agree. Now, to understand what is exactly happening, this is how you should look at it. This is the primary light source. S1 and S2 are the two slits which are going to behave like the derived coherent sources. Remember, I was talking about it some time back. Now, imagine the distance between the slits is small d. Okay, what is the distance between the slits? Small d. Then there is some point P on the screen which is at a distance of capital D or capital L over here. So usual symbols let's use. Usually it is capital D, and usually this capital D is much larger than small d. Okay, now think about it. If you move this point anywhere else, don't you see that the rays from these two slits will have to travel different paths, and hence the difference between their paths keeps changing. The path difference keeps changing if you move that point anywhere else. And you can visualize that very easily. If you make that point P over here, look at that. Both the rays will reach this point simultaneously. If they reach simultaneously, what is the path difference? Zero, nothing. That means, what should you get over there? Obviously, both of them reaching together, constructive interference. That means it's going to be a bright region. I hope that's clear. Yes, that's a bright region. Hi Parth, hi Roshu, welcome, all the new timers out here. Now, if you go far away, you can see, as you go really far away, all right, you can see both the rays almost become parallel. Think about it, both the rays almost become parallel, and once you are almost near infinity, think about it, once you are almost near infinity, can you guess what is the path difference approximately? Can you guess what is the path difference approximately if both the rays are almost parallel and going like that and meeting the screen at infinity? It's exactly equal to D. So that's the maximum path difference. This is the maximum path difference you can ever have. Yes, and over here the path difference will be 0 exactly at this point. So it starts from 0 and it goes till D. I hope that makes sense. Correct? So here it is 0, there it is D. So in between, you're going to have all sorts of values. And you will see that I can say then, one second. Yes. So I can say that on the screen, you're going to have 0. Some places you're going to have lambda by 2. Some places you're going to have lambda. Some places you're going to have 3 lambda by 2. Some place again you might have 2 lambda, and so on and so forth. And the same thing is also going to continue down. Do not forget that. Lambda by 2, then lambda, and so on and so forth. What are these? These are path differences on the screen. So guys, think about it. When it is 0 or lambda or 2 lambda or lambda, what kind of interference will it be? Come on, write it up in the chat box. We're going to start the 12th syllabus by April. Alright? Don't worry, by March, April around, we'll be starting it. So what will this kind of interference be? Yes, constructive interference. And all these locations, 3 lambda by 2, lambda by 2, lambda by 2, 3 lambda by 2, 5 lambda by 2, any odd lambda by 2, that will be destructive interference. And remember, the other name for these regions is called as minima, or basically dark regions. And the other name for these constructive interference regions is maxima, and they are also the bright regions on the screen, which we just saw. Keep this in mind. Very useful. Ankit, this is more like one shot. This is more like revision, more like concise manner, but as a full-fledged, all right, we'll be teaching like in a very detailed manner, all right, again for the 12th standard students, those 12th standard students who will be coming from 11th, right from March or April around. All right. Okay. So having said this, let's remove all these things and see some more formulas. The difference in the path, very, very important. The path difference, path difference, which is S2P, this point to that point, minus S1P, all right, whichever is bigger, that delta x is always going to be d sine theta. Now you might be wondering what the hell is theta. Keep this in mind, very, very important term. Theta is the angular position of point on screen. You can see if theta is 0, you are there. If theta is 1 radian, 2 radian, so like that. So as the radians increase, your angular position keeps changing. You can see that. That's d sine theta. That extra length S2 has to travel, or any other wave has to travel from that slit, is d sine theta. Keep this in mind. Keep this in mind. Don't worry, Ankit, even if you study 2 times, you're not going to, it's not going to be destructive, it's going to be constructive. Keep this in mind. So if you learn again from me and again in detail, in fact, it's going to be constructive interference. I hope that makes sense, Ankit. All right, cool. Now, having said that, also keep few things in mind, because this distance, I just told you some time back, this distance is much, much larger than this distance. You know, these angles are usually very small. Usually they are very small, and that's why you can approximately say sine theta is tan theta is also equal to theta, and that is equal to tan theta. Tan theta is opposite by adjacent, which is y divided by d. So this approximation is also useful certain times when theta is very small. Remember, and that will be small when this is very large as compared to this and all that. Now, having said that, the last formula, fringe width. Remember fringe width? One maxima to next maxima, or one minima to next minima. That's called as the fringe width. So, fringe width. The symbol for that is usually beta, and the formula is lambda capital D divided by small d. Do you remember I just told you the distance between the fringes depends on this distance, wavelength, and the distance between the slits. So you can see all of them out here. So this is the fringe width. So these are the formulas you should keep in mind in Ydse. Very, very important. Now, do you want to see the modified form of Ydse? Because questions from them also come sometimes as a difficult question. All right, so let me show you. What's it, guys? Should I show you the modified form of Ydse? Cool. Have you written down all these things? Excellent. Now, in this form, you will see the slits S1, S2 are parallel to the screen. But there is a second scenario, and there have been situations in JEE examination where this has been asked, even in BitSat for that matter. The slits are not parallel, but they are perpendicular, something like this. Like this. Now, this slit and this slit both emit wavefronts, and the waves do not reach the screen simultaneously this time again, unfortunately. And let's say I label this as S1, I label this as S2, and this is the distance between the sources, slits I would say, D, and this is our usual capital D, which is much, much larger than small d. Huge distance, this is like 3-4 meters, and this is like 2-3 millimeters. It's like 2 sources here and that screen here. It's hardly going to matter. This is such a big distance, and the distance between the 2 sources is hardly anything. That's how it is. In those situations, you will see, if you take any point P on the screen, the path difference, very, very important, path difference again, which would be again modulus of S1P minus S2P. This time it's slightly different. Keep this in mind. Delta x is d cos theta. Be careful. Over there it was sine theta. Here it is cos theta, where theta is this angle. Remember, both these lines are approximately the same because this distance is very small. So this is the theta, which is again the angular position of that point. Yes. Now the only change is that usually in that previous diagram, when the slits were parallel, one slit was here, one slit was here. Okay. Then what happens is that if the screen is like this, then these regions will be bright, one region will be dark. So you are going to get bands. What are you going to get? Bands or fringes, I would say. These are the fringes that you're going to get on the screen. But when the sources are perpendicular, think about it, both these lines meet at point P, and there will be many more points like that on the screen. If you rotate it about this axis, just rotate these two lines, visualize this, rotate it about those two lines, and you will see there will be so many points with the same path difference. So what is it going to form? It's going to form a circle. So you will see rings, not bands. You will see rings, not bands on the screen. So that's the big change. And in this time, if this is the radius, the only difference now will be, think about it, tan of theta. What would be tan of theta be equal to? Tan theta will be equal to this radius. Yes, this radius divided by the base, which is r divided by capital D. So that's the big change which is going to happen. Understood? So be careful. Remember this. Keep in mind. One last thing. This is very tricky question. I'm not sure how many of you get it, but if you get it, bang on. Very good. Congratulations. Let's see how many of you get this. My question to you is, let's say the distance between the slits is small d, and this is huge. This is much, much larger than small d. My question is, if you are here at this point, let's say O, I hope you can see that. What is the path difference at O? These are the two sources, S1 and S2. If both these light rays merge at point O, what is the path difference at O? Come on, tell me the answer in the chat box out here. Come on, minions, let me know the answer in the chat box out there. What is the path difference at point O? Come on, think about it. What will be the path difference of both these rays which will meet at O from S1 and S2? Excellent, Shreya and Sanspriya and everyone. Yes, Saurabh. Very good, Princey. Excellent, you have aced it. Perfect. JEE advanced type question. So it is D. Very good. So the path difference is D over here, and when I go really far, so here delta x is D, and when I go really far, can you guess at infinity what is the path difference at infinity? Come on guys, think and tell me what is the path difference at infinity. Come on, think about it. Bang. Come on. Very good. Excellent, Science Priya. Excellent. Very good, Kushi. Very good, Diya. Very good, Ankit. Excellent path. Excellent, PK. Yes, it's going to be 0. Do you see the difference? It's exactly opposite. For parallel, all right, it starts from 0 and goes till D. For perpendicular, it starts from 0 there and comes to D over here. That's the big difference. Very good, Spash. Very good, Aishwarya. Excellent. So that's the catch, and that's what you should remember. Keep this in mind. All these should be in your notes. All this should be in your notes. What a lovely concept. So when it is parallel, it's somewhere else. It starts from somewhere else, and when it is perpendicular, it starts from somewhere else. Okay, let's get going with the next question now. There are only questions. Let's see how many of you minions can do this. Very good, Yalni. Excellent. This was actually good concepts, by the way. Yeah. In a Young's double slit experiment, 16 fringes are observed in a certain segment. So you just imagine a certain segment, 16 fringes are seen, okay. When light of certain wavelength is used, now if you change the color to 400 nanometers, so how many fringes will be seen in that same segment of the screen? Come on, think about it. Very good, SP, very good, Princey. All right, Ankit says B. I don't know, let's see. Come on. Think about it. What will be the number of fringes seen in those particular segment? Okay, let's start solving. And if you do not want to see or look at my solution, you're free to do that. I'll be solving it neatly out here. Krishi says 28. Yalini says D. All right, Princey also says D. So fringe width, no Saurabh. Fringe width for perpendicular setup is not going to be same, because it is a cos theta, and remember sin theta is tan theta, but cos theta is not tan theta when theta is small. So you need to solve it using trigonometry. So from cos you can find tan using trigonometric formulas. So that's how it needs to be done. So there is nothing like fringe width for perpendicular ones. Good, you asked that question. Okay, I hope I answered that doubt. Now let's see how to do this. So imagine there is a certain segment. Let's say I call it length L. If there are 16 fringes here, so 16 times of fringe width of the first wavelength used should be equal to the total length. All right, 16 times beta 1 should be equal to the total length, which will also be some n number of times beta 2. Both of them must be equal, guys. So let's substitute the formula of fringe width, lambda d by d, and this should be n times some other lambda, same d by d. dd goes, and I will have lambda 2 is equal to 16 lambda 1 by lambda 2, and that's fine. So therefore lambda 2 is 16 times, what is n1? n1 is, where did it go, 700. And what is, sorry, lambda 1 is 700, and what is lambda 2? Lambda 2 is 400. 0 0 goes, 0 0 goes, 4 and 16 goes with 4, 7 4s are 28, and that should be our answer. Very good, Priyanka, very good, Kushi, very good, Prajakta. Yeah, I'm guessing you guys have answered it correctly. D. Excelente. Okay, let's get going to the next question, and here it comes. 2016 question in Young's double slit experiment. Again, Ydse. The distance between the slits and the screen, that means capital D, is 1 meter. Monochromatic. What is the meaning of monochromatic? Meaning single color, single wavelength, no multiple colors. Okay. 600 nanometers standard. Okay. A person standing near the slits, looking at the pattern, sees the separation between the slits is varied, and the interference pattern disappears for a particular distance d0 between the slits. Yes, the interference pattern disappears for a particular distance between the slits, small d, that d is d0. The angular resolution of I is 1 by 60 degrees. So what is the value of the distance between the slits? Now let's try and understand what the hell is this. Guys, I have a question for you. Have you seen those beautiful advertisements of, I don't know, maybe a cricketer, maybe an actor or actress on a big banner somewhere on a mall, or maybe over a building, or maybe just by the side of the road? Have you seen that? Now it looks so beautiful. Maybe, maybe it's Sachin's photo, or maybe Dhoni's or Virat Kohli's photo, and maybe he's posing with his bat. It looks very nice. It looks crisp, crystal clear, everything. Now, do one thing someday when you're free. Go very close to the billboard, alright, and see how that image is. You will be surprised to see it's not a continuous print. Yes, there will be dots over there. There will be, I say, spaces, and there are blank spaces in between. You'll be like, why don't I see that blank space? Because of the distance. If you go very far, your eye cannot resolve between those 2 points. They seem like virtually the same point, and it feels like a continuous smooth image. The same thing happens even on the prints of your books. If you observe it under the microscope, there is some gap. That's how it is. Yeah, there is a dot 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 thing, correct? So that is the meaning of resolution. I hope that makes sense. So that is what has happened here. The distance between those 2 fringes has gone so small that the eye is not able to distinguish. And you feel that, oh, that interference is not happening because that person's eye power is like that. So eye also has a resolution power, and this guy has a resolution power of 1 by 60 degrees. So let's see, how do we do this? Well, I guess it's not so difficult after all. See, think about it. If this is our screen, okay, if this is our screen, and I say that there is a fringe here, all right, there is a maxima here, okay, and there is another maxima here, okay, then this distance is basically fringe width, beta. Now think about it. If you are here, this is where the slits are, do not forget, this is where the slits are, okay, S1 and S2, and I tell you this distance is D, and a person standing here, or his eye is over here, he is not able to distinguish between these 2 fringes. That means the angle between them, what is the angle between them, guys? Exactly this one. So this is 1 divided by 60 degrees. I hope that makes sense. So that angle is 1 divided by 60 degrees. So that's why he is not able to distinguish them. Is that clear? Now things are very simple. Let's say I assume this angle to be theta. Just assume it to be theta. Very good, Khushi. Excellent. I'm just explaining this problem really slow so that everybody understands. So guys, how do I do this? Oh, I know what to do. Tan theta, guys. So tan theta is this by this, opposite, beta divided by this. And what next? Okay, theta is small, so tan of theta will be theta. So this is approximately theta, and beta is lambda d by small d, and this d comes over here. These 2 d's vanish. What is asked? D. All right. So d is basically lambda by theta. Now just substitute the values, but be careful. This is where most of the people make the mistake. I'll just remove this now. This is no longer needed. Most of the people make the mistake here. D is lambda. Where is lambda? 600 nanometers. Theta is 1 by 60 degrees. Be careful. Tan theta is theta only when theta is in radians, not in degrees. Keep this in mind. Common mistake, common silly mistake. Don't do this. Convert degrees into radians. How do we do that? Into pi divided by 180. Now do this math. You're going to get it. Nirama, I'm very good. Excellent. Anish, we have a dedicated crash course beta for CBSE plus what do you say, JEE. So I would request you to please join that, because we'll be dealing with all the chapters in more than 100 sessions specially dedicated for CBSE, and some 45 sessions just dedicated for, you know, what do you say, JEE. So I feel that you should join that so that you will be able to solve all these kind of problems which are there at the back of NCERT exercise, because theory, derivations, all these things will be done over there in that crash course. So if you want, just ping me on Instagram, Shreyas_Vedantu. I'll tell you more about it, or put up a comment after the video ends below the video and I'll respond to that. Okay, cool. Yes, so this is how it looks like, guys, and the answer comes out to be 2 millimeters. Okay, so that's how you get 2 millimeters. Let's get going to the next one. No problem, dear. I hope you'll join in soon. Yes. Saurav, marathon beta. Acha, Anish, then you can, if you're already in the JEE course, then yeah, you could have enrolled in the CBSE course also. Just talk and see if you can get yourself converted into the CBSE crash course as well. Talk to your student account manager or something. Just check it out. All right, let's get going to the next one. 2019 question in Ydse. Slit separation is 0.1. Observer sees a bright fringe at an angle of 1 by 40 radians by using a light wave of wavelength lambda 1. When the wavelength changes to lambda 2, then at the same angle you see a bright fringe. If lambda 1 and lambda 2 are in the visible range is given, then which of the following values are possible values for lambda 1 and lambda 2? Let's see this. Come on, let's see this. How to do this? Very interesting question this is. This is slightly interesting because I'll tell you there is a nice calculation in this, small calculation, but interesting one. Now let's see what is happening. Slit separation small d is given. Bright fringe is observed at an angle of something is given. Okay, so let me just draw the rough setup so that we get a rough idea of what is exactly happening. So this is our setup, guys. Okay, this is, let's say, O. This is where our two slits are, S1, S2. This is our screen, of course. And at certain angle, maybe let's say theta, at this particular point, you see a bright fringe over there. Okay, so you are seeing a bright fringe over there. Okay, and that angle is also given. Distance between the slits is also given. Now let's see what is exactly going to happen. Okay, so I will try and recollect some formulas. For path difference, what is the formula? The path difference formula delta x is just d sine theta. For it to be bright, this delta x must be n lambda. Isn't that correct? For it to be bright, it should be n lambda. So therefore, lambda is equal to d. D is 0.1 millimeter. So 0.1 into 10 to the power minus, what the hell is that? Millimeters, yes. Into sine theta. Sine theta will be theta only because theta is very small. So it will be just d theta approximately. And what is the value of theta? It is 1 divided by 40 divided by n. Now what will this come out to be? This will come out to be lambda is equal to, you can do the math, just check it out, how much you are getting. Check it out, how much are you getting? I'm pretty sure you will get it as something like 2500 into 10 to the power minus 9 meters, which is 2500 nanometers approximately. So this is what you should get. Check this out. And the whole thing divided by n, of course. Whole thing divided by n. Don't worry, this n and this n will not cancel out. If you want, I will just put or make this as capital N so that there is no confusion. Okay. Now comes the interesting part. Only certain wavelengths which follow this relationship will give you a constructive interference or a bright region. That's what this formula tells me. For this particular angle, which is 1 by 40 radians, the path difference, if it is n lambda, that means it will be bright, and only these wavelengths which obey this relationship will give you a bright region exactly at the same spot. Now think about it. What are the different values of lambda that you can get? Just put n as 1. You will get it as 2500 divided by 1. Then you will get it 2500 divided by 2. Then you will get 2500 divided by 3. 2500 divided by 4. 2500 divided by 5. 2500 divided by 6. You will get all these wavelengths which will give you constructive interference at that same angle. I put that angle. The angle is not changing. So now just calculate the values. 2500 nanometers. Correct, guys? I hope this is clear. Everybody understanding this, minions? Come on, think about it. Everybody understanding it? So 2500 divided by 2. How much is it? 1250 nanometers. Then divided by 3. 2500 divided by 3, guys. Yes, come on, think about it. Yeah, 3 approximately nanometers. Then divided by 4, guys. Come on, 2500 divided by 4. Come on, think about it. Which other values will come? Divided by 4. 4 6 are 24. So 6, then 2, and then 5 nanometers. And then 2500 divided by 5, it will be 500 nanometers. And then 2500 divided by 6, guys, come on, think about it. Yes, come on. 6 4s are 4, and then 1 and 6 nanometers approximately. So do you see which of them fall under this range? I think only few of them are falling under this range. 625, 500 and 416. That's it. 625, you can see that. 625, 500 and 416. These are the only 3 wavelengths under that range. So that's it. Choose the options based on that. Okay, only there are 2 wavelengths in the given options. That's the answer. Correcto. Excellent. Understood how this question had to be solved? The whole idea was at that same point, because the point is given to be the same, alright, because the angle is the same, you are going to have the same part difference but for different wavelengths. That's the whole idea. Cool. Anish, I'm simultaneously doing modern physics. Like you can see, I will start with modern physics, in fact, tonight at 10 o'clock, and that would be almost the end of the portion. Maybe semiconductors and some basic things might be remaining. So I will do it on and off. Don't worry. But otherwise, 95%, 99% of the portion will be done. All right. I hope that makes sense. Cool. Here's the next question, 2012 question. In a Young's double slit experiment, the slit widths are, the slits widths are in the ratio of 1:25. Then the ratio of the intensity of maxima and minima of that interference pattern is which of the following? Check this out. Which of the following? All right, come on. Let's see how many of you get this. Okay, let's do this. I'm going to start doing it. You can take a screenshot so that you know which are the options, but I'm going to start solving this. Now, remember one thing. If the width of a slit, okay, this is the width of a slit. So, this is opaque, only this part is open. If the width of the slit changes, think what will happen. There will be more light or less light coming out of it. That's it. So basically the intensity is directly proportional to the width of the slit. Keep this in mind. The intensity, more the light, more the intensity, and more the width. That's how it works. Now recollect what had I just given to you, I max by I minimum. I just told you, just in one of the previous questions, in case you have arrived late, just rewind back the lecture a little bit. I've done this in one of the previous questions. Is root of I1 plus root of I2 whole square, and I minimum is root of I1 minus root of I2 whole square. And that ratio is given to be 1:25. Max by min will be 25 by 1. So 25 by 1. So take the square roots, guys. Yes, just take the square roots. Oh, one second. And I did a mistake, guys. Sorry. This is not 25:1. So sorry. In fact, this is what we have to find. So sorry. I1 and I2 are the intensities of the individual slits. So sorry. So this will be basically I max by I minimum. Yes. So this will be I max divided by I minimum. My bad. I1 and I2. Okay. So what are they in the ratio of? 25:1. So this will become root of 25 plus root of 1 whole square divided by root of 25 minus root of 1 whole square. That is I max by I minimum. So solving it further, I max by I minimum will be root 25 5, root 1 1, root 25 5, root 1 1 whole square. So 5 plus 1 6, 5 minus 1 4 whole square, 6 by 4 3 by 2 whole square, which is 9 by 4. That's the answer. Yes, that's how it is. Okay, yes, that's the answer. Make sense? So intensity of slits, 2 slits were of different intensity, so that's why I1 and I2 will be proportional to the slit widths, 25 and 1, and that's how I solve the question. That's the way you do it. 9:4, 2012 question. Next question coming up on your screen. Come on, guys, let's do this. Hardly few questions left. Come on, come on, come on, come on. Let's do this. Let's do this. At 2 points P and Q on the screen. I hope you guys are not tired. And if you are tired, you can take a short water break, because it's not going to be a very long session also. Believe me, more 20-30 minutes. That's it max. Very good, Brajesh. Glad I can also interact with you guys. I'll see you, Brajesh, on Monday again. Okay, so some of you have already given the answer. Well, let's see what's the correct answer for this. Okay, so 2 points on the screen. All right. The first point. Okay, so for point P, so at point P, what will be the phase difference? Well, at point P, the path difference is given to be 0. So that means the phase difference will be 0. Cool. So that means the intensity at point P will be I1 plus I2. And because it's a double slit experiment, that means I1 will be equal to I2 is equal to I. Usually both the slits are of the same width. So it will be I1 plus I2 plus 2 root I1 I2 cos 0. So that's going to give me cos 0 is 1. I square's root is I. 2I plus I is going to be 4I. So that's what IP is going to be. Okay, so that's what IP is going to be. Next, for that point Q, the path difference is lambda by 4. So the phase difference for point Q will be 2 pi divided by lambda into path difference, which is pi by 2. Okay, so intensity at point Q will be I1 plus I2 plus 2 root I1 I2 cos 90 degrees. Cos 90, 0. This whole term vanishes. So I plus 0 is just going to be 2I. So the question was, what is the ratio of this divided by this? So 4 divided by 2 is 2. 2 is to 1. Yes, very good, excellent. That's how you do this. I hope you realize the problems are not difficult, but there are so many questions asked in the previous years, and I'm just taking a small sample of it. You have to make sure that you solve all these questions now that you know the theory. I'm giving you these problems so that you know how to apply the concepts, how to apply the formulas, because just learning the theory is of no use. That's why I'm solving these problems on my own over here, so that you observe me and learn how to solve the problems. That's very important. 2:1. Here comes the next question. Beautiful question, 2004 question. The maximum number of possible maximas for a double slit experiment where the slit separation, that is small d, is 3 times the wavelength, then how many number of maximas will you see on the screen? Very useful, very important theory. Yes, Omkar, you can do that if you want to remember that formula, that is, else it's very straightforward. Okay, so let's see how to do this. 3, 5, infinite, 0. How many number of maximas will be seen on the screen? 3, 5, infinite or 0. Okay, now I'll tell you how to solve this. Just some time back, I told you about that, if, for example, this is our screen and this is a point directly in front of the screen, all right? At that point, you are going to see 0 path difference, okay? And that's why it's going to be constructive, or I can say a maximum. It's going to be a maximum. Now, remember I told that at O, the path difference is 0, but as you go far away, the path difference increases, and as you keep on going far, you can see the path difference. One of the rays has to travel more than the other. It keeps increasing, and remember, when you reach infinity, if this is S1 and if this is S2, delta X tends towards D. It tends towards D, the distance between the slits. So what is the distance between the slits? Think about it. The distance between the slits is thrice the wavelength. So at infinity, all right, you are going to get the path difference delta x tending towards 3 lambda. It will not be equal to, but it will be tending towards 3 lambda at infinity. That means somewhere here you're going to have 1 lambda and somewhere here you're going to have 2 lambda, and whatever happens on the top happens below. So this will be 1 lambda here and 2 lambda here. Is that making sense? And again at infinity you're going to have 3 lambda. Now remember, infinity is a polite way of saying never. If I tell you I will meet you at t tends to infinity, that's a polite mathematical way of saying that I'm not going to meet you. I hope you get my point. So guys, now you just do the basic counting and you can measure it. 1, 2, 3, 4, 5. So you're going to have 5 maximas. Yes, you're going to have 5 maximas. I hope that makes sense. Very good. Excelente. And that's the answer. That's the answer. 5. Understood, guys? So infinity is never going to happen. So count everything else that happens before that infinity, and do not forget that central or that maxima at the origin, or else you'll miss one. Alright, let's get going. Next question. Beautiful question. Don't get scared looking at the options again. The figure shows again a standard YDAC setup. This is the distance between the slits. This is the screen. This is the distance between slits and the screen. Okay. Now there is a thin transparent sheet, some thickness, some refractive index, and it is put in front of it. Now the central maxima gets shifted by some distance which is equal to n times the fringe width. N is also given to you. The question is, what is the thickness of the sheet which was introduced? Rajendra, I am great. Hello Yavar, I guess you are a little bit late today. Join in, it's okay, you can watch the replay later on. Now I'll tell you what is happening in this question. Beautiful question, and a lot of people get confused in these kind of questions. They mug up some kind of a formula. Guys, don't be that student who is going to mug up formulas. See, try and understand what is happening. Imagine that there was no slab over there. If there was no slab over there, what's going to happen? Both the rays will meet simultaneously at this point O. Isn't that right? Both the rays are going to meet at this point O. Now, if you introduce a thin glass slab here, alright, a glass slab over here, think about it and tell me, will both the rays simultaneously meet at point O? Yes or no? Because of the glass slab in front of this slit on the top, do you think they will meet simultaneously at point O? I'm not interested in the answer, but let's see how to do this. No. Okay. Now my point is, where will they meet simultaneously? Will they meet simultaneously at a point on the top, or will they meet simultaneously at a point below point O? Will they meet at the point on the top or at a point below? Think about it. Yes, there will be a shift, but where will the shift be? Will that meeting point be on the top simultaneously, or will it be below? Think about it. Think about it. Because the glass slab will slow down Brajendra Kumar. It will slow it down. The ray of light will be slowed down in the glass slab. So they will not meet simultaneously. Yes, above on the top. Because, think about it, because this ray passing through the slab has slowed down, you have to give it some kind of a bonus, a plus point, an advantage over the other ray. So what you do is make the other ray travel little bit longer distance than usual. So this ray has to travel shorter distance and this ray has to travel longer distance. So whatever time it spends in here, it's compensated by the longer distance traveled by the other ray. I hope this makes sense. Correct? Now, if that angle, alright, if that angle which it makes is theta, guys, we know that at this particular point, okay, let's say this is that point, and this is that shift, of course. Okay, this is that shift. So think about it. Think about it. The net path difference at point P is going to be 0, guys. Believe me. Why? Because whatever ray 1 slowed down is compensated by the extra distance ray 2 has to travel more. So it is compensated, and hence the net path difference at that point P is 0 because both the rays arrive simultaneously. And what is the net path difference? The path difference because of the slab plus the path difference because of the distance actually. One is traveling more than the other, and this is 0. And now think about it. What is the path difference because of the slab? I just told you, thickness into refractive index minus 1. Isn't that right? Thickness into refractive index minus 1. I just told you at the beginning of the class. And the other one, do not put a plus sign. Put a minus sign, because if one is moving ahead, the other one will be moving behind. If delta x is positive here, delta x will be negative here, so that the addition will be 0. So guys, what are you going to get? D sine theta. Remember, that's the path difference. I just told you while solving Young's double slit problems, if you have this point, this path difference is always d sine theta. Keep this in mind. And now that's it. Solve this. T into mu minus 1 is equal to d sine theta, but sine theta is approximately tan theta, and tan theta is opposite by adjacent. And what is opposite is the shift. All right, it's the shift divided by d, and therefore, all right, I don't need this anymore. Okay, so I'll do it here probably. So think about it. T into mu minus 1 is equal to, what is the shift? Shift is given n fringe widths. So n times of beta. N times of beta divided by d. Now what is beta? Beta is a lambda d by small d. That's capital D is also here. dd goes. And what have you been asked? You have been asked t. So that is t into mu minus 1. So therefore t will be n lambda divided by d into mu minus 1. That's the answer. Correcto. Very good, Khushi. You have been fast. Excellent. That's how you do this. Understood, guys? This is a logical way of doing it. Yes. Cool. Let's get going ahead with the next question now. Okay. Now let's talk about the last part today, and that is diffraction. And yes, we have solved so many problems on Young's double slit experiment. So let's solve problems on diffraction. By the way, this is a very cool example of diffraction. Whenever light passes through a narrow gap, it spreads, and that spreading of light is called as diffraction. It bends, the light spreads. And why is it happening? Let's talk about it. See guys, there is a very simple way of explaining this, and I want you to understand that. Look at this. Light is coming from this side, left side, and there is a small opening here. I hope you can see that. The blue one is a obstruction, and there is a small opening out here. Now, remember, whenever you have an opening, it behaves like a secondary source, and it emits new wavefronts. Each point on that opening will act like a source now. Now, the thing is, since the slit itself is wide, there are no two slits, it's a single slit. Keep this in mind. Since the slit itself is wide, there are many points on it. You can see those red dots. Each of those red dots will behave like a secondary source, and they will emit secondary wavefronts and treat them like many Young's double slit experiment. Yes, treat this and this as a double slit, this and this as a double slit, this and this as a double slit. So there are so many slits. Think of it like that. So there will be a combined interference pattern produced on the screen. And you can see some places are interfering constructively, some places there is nothing, that's destructive, again constructive, that's fainter, again destructive, constructive. So on the screen, the pattern that you will get will be very much similar to Young's double slit experiment pattern, but it is called as a diffraction pattern or a single slit pattern because there is only one slit here, and in that slit all those points between those two edges have acted like secondary sources, which in turn produce interference. I hope that makes sense. And the light bends. And now, if you change the width of the slit, the light will bend more or less. And we're going to see that formula. If this is clear, so this is how the pattern looks like. You can see light enters the slit, it spreads, and you will see a diffraction pattern on the screen. Bright, dark, etc. The central bright is really bright. Pranav, the topic is whatever is mentioned. I mean, like Young's double slit experiment, interference, optical path difference, diffraction and all that. Now we have come almost towards the end, but you can catch up definitely, Pranav, by watching the replay. Don't worry. Okay, and it's a very important topic. We have done so many problems today on previous years. So if you have a slit of width D, and if this is the screen, this is the diffraction pattern. So let me tell you, very important formula out here. Okay, so let's say this point, let's say this is the angle, okay, theta. Like you can see, this point is a point where there is a minima. Now the formula is only for minima, which you should remember. All those points, d sine theta, keep this in mind guys, very important formula which you should remember. D sine theta will be equal to n times of lambda. This is the formula for finding, keep this in mind, this is angular position of minima, and okay, I can use small d also or capital D, depends. So let me put capital D because the symbol used over here was capital D. I don't want any confusion out there. So d sine theta is equal to n lambda. That's the formula which you are going to use for minima. Keep this in mind. So if n is 1, you will get the first minima. If you get n as 2, you will get the second minima. If you put theta as 0, you will not get any minima. I mean, there is no minima at theta is equal to 0. Keep this in mind. Yes, that's how it is. Yes, Arnav. So here the symbol has changed. So if you want, and if you are getting confused, don't worry. Keep it as small d. And let's do one thing. Let's erase this and write it as small d. And let me put this as capital D. Okay, I hope now it's fine. Okay, cool. Yes. Hello, Swapnil. Wow, Ramesh, welcome. You were searching the right thing and you are here at the right moment. But you are a little bit late, Ramesh, but you can watch the entire replay of this lecture. Do not forget to hit the subscribe button so that you do not miss the next few lectures, which are very important. And do not forget to hit the like button as well. Now the next important formula is for a hole. See, the previous formula was for a slit. But when there is a hole, the pattern is going to be circular. Yes, you're going to get circular rings. That's a circular aperture diffraction pattern. And the formula for that you should remember again, but only for the first minima. You have the formula only for the first minima, guys, not for the second or the third minima. Keep this in mind, only for first minima. Keep this in mind. And the formula is d sine of theta is 1.22 lambda. And now you might be wondering, what the hell is d? This d is the diameter. Yes, this is the diameter of the hole, of that hole through which the light bends and you see a diffraction pattern. So that's what is going to happen. Is that clear? So keep this formula in mind. This is very important. D, which is diameter, sine theta. Theta is the angular position where you are going to get the first minima is 1.22 times the wavelength. Keep this in mind. Okay, let's solve a problem so that you get a hang of this. This was asked in 2017. Single slit of width 0.1 millimeter is illuminated, okay, by a parallel beam of light, and wavelength is also given. Diffraction is observed on a screen at a distance of 0.5 meters from the slit. The distance of the third dark band from the central bright band is how many millimeters? Let's do this. Oops, I don't want to see the answer, guys. I don't know. Okay. Let's do this. It's not that difficult. Okay. So this is our screen. This is our slit. Okay. This is our slit, and it has some width D, and this distance is capital D. Okay. This is your first maxima out here. Okay. And then you're going to get your minimas. So you're going to get your first minima, then second minima, and of course your third minima. And what they have asked, the distance of the third dark band from the central bright band. Okay, so here is what I'm going to do. I'll join this line, I'll mark this angle as theta. Okay, and they have asked us this distance. How much is this y? How much is this y? That's what they have asked. So what I can do, I can say tan theta is y by d. Oops, capital D. Okay, therefore y is d tan theta. But do not forget that tan theta is approximately equal to sine of theta. So I can do that. Tan theta is sine theta. Now the next part, remember the formula of diffraction single slit? I just told you small d sine theta is n lambda. Which dark band are we talking about? We are talking about the third dark band. That means small d sine theta is 3 lambda. So therefore d sine theta is, just sine theta is 3 lambda by small d. Just substitute it over here and you will get the answer, guys. So therefore y will be equal to d multiplied by 3 lambda by small d. Now you know everything in the problem, just substitute. Distance 0.5 into 3 into how many Armstrongs? Okay, 6,000. So 6,000 into 10 to the power minus 10, and the whole thing divided by width of the slit. It's 0.1, but that's millimeters. So into 10 to the power minus 3. So just do that and you'll get the answer. Very good. So that's how you do this. I hope this problem is not so difficult once you know the theory and the formula. That's about it. Just substitute the values and check out what you are getting. What are you getting, guys? I think you should get it as 9 millimeters. Just check it out. I mean, use my trick. Do you remember the trick which I told you some days back? If you have not seen that trick, try to see that video again. I have given 7 important tricks which toppers use. Guys, look at these numbers. 5, 3, 6. 5 3s are 15. 15 6s are 90. So don't worry about the zeros. The answer will be something 9 or 9 something. So where is 9? This. That's it. Mark it. Done. Do you remember this trick? I have given you this trick in those 7 pointers which I have talked about in one of the previous videos. It's just a 9-minute video. Watch it. Watch all the 7 pointers which I have given. So that's how you can do it. All right. So some questions for homework which are there in the session PDF. You can download the session PDF from the description box or from our Telegram group. These questions have to be tried at home. The answers and the solutions are mentioned. Do not look at the solutions before you make sure that you have attempted it wholeheartedly on your own. All right. So 3 questions, very important questions, along with solutions have been given. You can download the entire PDF by joining our Telegram group, where you will get all the official important updates. And do not forget, the crash course is also starting on Monday, and the crash course right now for JEE is running on a special discount of 30%. The usual discount was 20%. So do not forget to join it over there. The link for that is in the description box below. Use the coupon code SHCC to join the crash course for with this discount. Yes. See you guys at 10 o'clock now. Have some dinner, gain some strength. See you at 10 o'clock, and do not forget to subscribe and love this video and share this video with your friends, and yeah, spread the joy of learning. Bye bye. This was Shreyas here, your master teacher.